This is my first visit to Singapore. It's really a pleasure to be here. Exciting place, and I've heard a lot about CQT over the years, and so it's also exciting to come here, and I've had a lot of good discussions with people. And I want to tell you about our work towards scalable quantum computing with atoms, and I'll try and give you a mix of some atomic physics ideas and results, and their connection with working towards quantum computation. And so I've divided this talk up into a few parts. I'll tell you a bit about neutral atom qubits and this by now very well-known idea of Rydberg blockade for creating entanglement between atoms. And I'll tell you about making arrays of these atomic qubits, qubit arrays. And then I'll tell you about some new ideas we're working on now using some of the more complex atoms in the periodic table, which we think are going to provide some solutions to some of the outstanding challenges of a neutral atom-based quantum computer. And I welcome you to interrupt me or try and interrupt me as I go along. I'm very happy to have a discussion about these things as we proceed. So let me get into it then with just an introduction to the atomic physics side of things, which is this notion of working with Rydberg atoms. And by Rydberg atom, we mean simply a very highly excited eigenstate of an atom. Here's the level diagram of cesium. This is the ground state where we have hyperfine structure, we encode qubits, and then these are the excited states, and any of these levels up here can be a Rydberg level. And what's special about the atoms excited to Rydberg states is that they have very exaggerated properties. The size of the electronic wave function scales as n squared times a Bohr radius, n being the principal quantum number. And so when we get up to n around 100, these atoms have wave functions that are about 1.5 microns across. So these are relatively large atoms. And along with those large wave functions, we get large transition dipole matrix elements. And that results in the interaction between two atoms scaling as a high power of the principal quantum number. So the resonant dipole-dipole interaction scales like n to the fourth. The effective van der Waals interaction between two such Rydberg atoms scales as n to the 11th or even n to the 12th for the heavy alkalis. And it's the combination of these very large interaction coefficients together with lifetimes that also scale as the power of the principal quantum number, the combination of those two that is enabling for quantum information and creating entanglement. At the same time, we have some challenges. The sensitivity of these extended wave functions to background fields, as is quantified by the polarizability, that scales as n to the 7th. And that's not a feature, that's a challenge we have to meet. That is, we have to work with these atoms in a very quiet, field-free environment, not to be disturbed by background fields. So the basic idea in this area to use these Rydberg atoms for computation is the so-called Rydberg blockade, which is an atomic analog of the Coulomb blockade, that you can't put more than one charge through a narrow wire at a time because the charges repel each other. We have a similar effect in the Rydberg world. If I have a ground state atom and I couple it with a laser field with Rabi frequency omega up to a Rydberg state, well, I can excite a Rydberg atom. And if I have a second atom very far away, I can also simultaneously excite it to a Rydberg state. But as those atoms move closer together, their molecular energy lives on this curve, say a 1 over r to the 6 van der Waals curve. And if the atoms are too close together and I try and excite with the same frequency, I'll be off resonance. There'll be a blockade effect. And so this region in here, at a separation smaller than the blockade radius, it's forbidden to have two atoms simultaneously excited in that region because of the blockade effect. And so this blockade radius is not an intrinsic microscopic parameter of the atom. It's a combination of the C6 coefficient, which is an atomic parameter, relative to the excitation rate, which determines the width of this resonance line here. And so I can only excite one atom at a time at distances shorter than the blockade distance. And so with that notion in mind, there's a couple different regimes one can think about Rydberg blockade. And even before getting to that, it's worth thinking about, are there other AMO systems, other atomic or molecular systems, one could use for these kinds of experiments. And a way to compare things is to define a figure of merit, which I'm calling here J times tau, where J is a coherent coupling rate between atoms or molecules or ions, say situated in an array like this, and tau is an available coherence time. So this figure of merit is effectively the number of coherent operations I can perform in a coherence time on my atomic species of interest. And we might consider comparing ions, polar molecules, several groups here, and also many other places working on molecules, and also neutral atoms with different possible interaction mechanisms at play. They could be magnetic interactions, they could be collisional interactions, they could be these Rydberg atom interactions. And here's a plot showing this figure of merit, J times tau, for some different approaches as a function of the separation between two objects. And so for alkali atoms, one has magnetic dipole interactions that are quite weak. One can work with a highly magnetic atom, for example, dysprosium, which has 9.5 Bohr magnetic moment. It has a stronger magnetic interaction. One can have strong collisional interactions, but only at very short range. The atoms have to be essentially on top of each other. One can have polar molecules. Here's sodium, potassium on this curve here. And then here's Rydberg atoms excited to higher and higher states. And not surprisingly, I prepared the slide and I like Rydberg atoms. The Rydbergs come out as the winners. But if you go to high N with Rydberg atoms, you get a larger figure of merit than any of these other approaches. The challenge then is to manage the complexity of the multiple levels that we have in Rydberg excited atoms, and also their fragility or sensitivity to external fields. Okay, so using the strong interactions, we can go from ground state situation, which we can use to encode quantum states, and ground state atoms are very weakly interacting, and excite them to Rydberg levels and get these strong interactions. And what's remarkable is that the difference in interaction strength can be 12 orders of magnitude or so at 5 to 10 micron separation. And so the ability to turn an interaction on and off with that amount of contrast, 12 orders, is, I believe, unprecedented in other systems people are working with for quantum information. And so that Rydberg blockade capability has been used to create entanglement between pairs of atoms in several labs. It's been used to create entanglement between atoms and photons in historic experiments in the Hirosh group, and more recently by the Kuzmich group using atomic ensembles. And a current frontier is to use Rydberg blockade to effectively create a photon-photon gate. And that's not quite been done yet, but people are getting very close to that, and I expect we'll see results of that kind in the not too distant future. And there's also other things one can do with the Rydberg interactions. For example, create coupling or even entanglement between photons of different wavelengths, for example, microwave to optical. When He's group has made some very nice first steps in that direction here, creating conversion between microwave to optical photons using Rydberg interactions. So the Rydberg blockade mechanism prevents more than one atom at a time being Rydberg excited if they're too close together, yet there's a couple different regimes one can think about exploring with this interaction. Supposing I have a 2D array of atoms laid out, and I uniformly excite this entire array with some optical field coupling me up to a Rydberg state. There's a regime of weak interactions where the blockade distance is small compared to the lattice spacing, the separation of atoms. And in that regime, I can excite multiple atoms at the same time. And so if I illuminate the entire array, I'll simply excite all of these atoms up to the Rydberg state. That's an interesting regime for quantum sensors. Rydberg atoms are near ideal sensors for single photons. They can be microwave photons, they could be terahertz photons. So there's some opportunities in that regime for quantum sensors. There's an intermediate regime where the blockade distance is comparable to the lattice spacing. And in that regime, if you excite the entire array, the atoms will arrange themselves in a way that tends to minimize the free energy or maximize the average separation of the atoms. And so spatial correlations will naturally emerge in this kind of system that was shown in an experiment by the Block group in Munich some years ago. And then there's the regime of strong interactions where the blockade distance is large compared to the lattice spacing, and then we just excite a single Rydberg atom at a time. And so we might excite this atom, we might excite a different one, or yet another one, but from a quantum mechanical perspective, what we're really creating when we illuminate this entire array is a quantum superposition of any one of these atoms being excited. And so that's a many-body entangled state, what's referred to in the quantum information area as a W state, where I have a single excitation shared among all the atoms. And I'm not going to show you any details of that today, but this is an experiment we did some years ago, a couple years ago now in Madison, with a disordered ensemble, and it's also being done in Munich with an ordered array of this kind. And one can create many-body entanglement in this way in sort of a one-step process of more than 100 atoms. Just 1 second. And so that's one type of entanglement one can create with these Rydberg interactions. But I'm going to focus more on controlled entanglement between individual atoms, which we achieve by focusing our excitation beams down to individual sites in this array. And so if I have a beam exciting this atom, then whether or not that atom gets excited, if it's in the state that's coupled to the Rydberg state, can prevent excitation of a second atom, which leads to entanglement. And so we can perform quantum gates using that kind of approach. We could do quantum gates between neighbors. And then because the Rydberg interaction is long-ranged, we can do gates beyond nearest neighbor, which can be beneficial for connectivity in a larger array. We can also design protocols for multi-particle gates with these interactions. So we have protocols for C naught to the K, where excitation of a single Rydberg atom prevents excitation of any of its nearby neighbors. And so that's a C naught to the K. There's an even more interesting operation, which is the CK naught, where K control atoms control the dynamics of the quantum state of one target atom. And this type of multi-particle interaction is expensive to implement as a decomposition in 1 and 2 qubit gates, and turns out to have a lot of application in error correction circuits, for example. So this is also something we can do with Rydberg interactions. Okay, so that's the vision of sort of how one might think about using these interactions to build up a small quantum computer. The reality is, of course, a mess. It's one of these complicated setups with optical tables and lots of lasers and lots of optics and mechanics, and from a distance looks very much like some of the labs I've seen here. Beauty's in the eye of the beholder. When I look at these pictures, I think they look wonderful. When investors come by my lab and talk to me about developing quantum computers, they run away screaming and they say, it looks horrible. How are you going to make that practical and reliable? And that's something we're working on, but not the subject of today's talk. But we have these complicated setups to point laser beams in particular directions on these individual atoms. So let me show you some of the aspects of how we do this. We start with a pretty standard setup where we create cold atoms in a two-dimensional magneto-optical trap. We push them up into an all-glass cell where we have good optical access. We turn on beams and trap a few 100,000 cold atoms here. And then we project an optical lattice onto that magneto-optical trap. We use a kind of unusual lattice in my group, which you can think of as just a pattern of light intensity. So not an interference pattern, but just a spatial distribution of light. This is light of a wavelength that's blue detuned. It repels the atoms, so atoms are trapped in local minima of the intensity, and we create a 2D array of these minima, which traps atoms, and this is a picture of the fluorescence from those trapped atoms in a 2D array, and we have 49 sites right now. And then we have beam scanners set up that allow us to point various laser beams at individual sites to perform gates and control the circuits. So here's some data showing atom loading. In fact, we cannot deterministically load every single site. So this is raw data, and if we average that, we get these composite images, and then we can distinguish no atom and one atom by counting scattered photons with a camera. We'd like to deterministically load all of these sites. That's not something we've done, but other groups have shown that you can rearrange partially filled arrays into fully filled 1D arrays at Harvard and 2D arrays at Institut d'Optique in France, and we're currently working on adding this kind of capability to our system to fully load up these arrays. So our toolbox for doing quantum circuits are 1 and 2 qubit gates. We can perform gate operations on all qubits in parallel using microwaves, and then we can do single site gates with a combination of microwaves and optical addressing. And then the Rydberg blockade gives us a natural controlled Z gate, and then that plus local rotations gives us CX or C0 gates. So our qubits are encoded in the clock states, m equals 0 states of cesium, 9 gigahertz splitting, and then we have a variety of lasers for optical pumping and cooling and readout and 1-bit gates and 2-bit gates. So a lot of different laser colors go into these experiments. Here's an example of just microwave rotations on the qubits. I like showing this because it's something that's very easy to do in the lab. You just set up a synthesizer and a microwave horn and you turn it on, and all of these guys will rotate in parallel. We can look at this data a little bit more carefully and quantify the fidelity of these operations by doing randomized benchmarking. So we perform a sequence of random rotations, keep track of them, and then check that we end up in the correct spot. And then the error per rotation gives us an effective gate error. And we can hit about 3 nines doing this, so pretty good. We can also do local gate operations using focused laser beams. Here's some older data in a 1D array where we used 2-frequency Raman light focused onto individual sites. And we could do pretty fast rotations, 150 nanosecond pi time. And with focused light, we can rotate one site and do very little on neighboring sites. In the 2D array, we've taken a slightly different tack and combined the microwaves with the local Stark shifting laser. So if I detune the microwaves and then locally Stark shift 1 qubit into resonance, I can rotate that qubit without disturbing my neighbors. And then using beam scanners, we can do multiple sites at a time. So this is building up some of the tools we need for circuit operation. The fidelity here was only about 2 nines, a little bit worse because of additional noise introduced by this Stark shift laser. So what's the current status with these single qubit operations? This is kind of our progress in the last few years. This is a global addressing result from the Porto group. Dave Weiss has now done this in 3D, a little bit better than us. So there's been a good progress. More work is needed, but this is not the thing that keeps us up at night. We're confident that we can further improve these single qubit operations to get close to the sort of state-of-the-art 10 to the minus 6 error that's been demonstrated with trapped ions. More challenging is the 2-qubit gates. So this is the Rydberg interaction again. And the protocol for creating entanglement with the Rydberg interaction is this 3-pulse sequence. I excite a control qubit from the 1 state up to the Rydberg. I then do a conditional 2 pi on the target and return the control qubit back to the ground state. If the control qubit starts down here, this 2 pi rotation occurs and I pick up a pi phase. If the control qubit started here, it gets Rydberg excited, blocks this rotation, so I get a conditional phase. So that's my conditional Z gate. And in the ideal limit where this frequency and the blockade shift are large compared to my excitation rate, which is in turn large compared to my decay rate from the Rydberg state, I get an ideal controlled Z gate. Reality, of course, is not perfect, so there'll be some errors, but this is ideally what we would get. The apparatus for doing it is all the stuff we use for single qubit gates, plus some highly stabilized Rydberg lasers that we lock to cavities and have 100 hertz or so line width on. Okay, so here's a schematic of how we approach these Rydberg experiments. Again, we're using atoms trapped in this projected Gaussian beam array. A nice feature of this array is that it not only traps ground state atoms, but also traps Rydberg excited atoms. The Rydberg excited atom is, to first approximation, a free electron. This electron is a micron or so away from the nucleus. It's a negative charge, so that electron has a negative polarizability, and it's again trapped in this blue detuned lattice with a local minimum of the intensity. It's possible to design this so the trapping potential is the same for both the ground state and the excited state, a so-called magic condition, and that's something we've been able to observe in experiments, but we're not actively using in these experiments here. So we do a 2-photon excitation up to the Rydberg level. I can pick out a couple sites in the lattice that I focus my excitation beams on and observe Rabi oscillations between ground and Rydberg states on these two sites. And here we're working at next nearest neighbors, giving about 20 megahertz or so interaction. So the C0 sequence is the Rydberg pulses, the pi, 2 pi, pi Rydberg sequence, which is a controlled C, and we put that in between pi by 2 rotations on the target to get a controlled X. Now, there's some details of these Rydberg pulses that I didn't mention, which is there's some additional AC Stark shifts. So instead of getting this ideal pi phase shift, one gets the pi phase shift plus some additional phases from having these beams that are detuned from resonance. There's a detailed discussion of all that in this paper here. But in practice, what we do is we measure these eye diagrams. That is, we vary the relative phase of these two rotations and look at the target state that we end up in, and then we set the relative phase to sit at the maximum contrast of this eye diagram. And doing that, we get a C0 probability truth table, and additionally measuring the phases of the output states, we can determine a Bell state fidelity, which we've been able to push up to sort of mid 70% level. So what's the progress been on these entangling Rydberg gates? Not as clear as for the single qubit gates. These are the early experiments done around 2010, which the blue dots here are deterministic measurements. The open circles are data that's post-selected for loss of atoms. And then more recently, we've been able to improve our fidelity a bit, and there's also a couple other experiments now, but there's not been the kind of very strong improvement in error down to the state of the art, which is 10 to the minus 3 yet. So, what's going on with this? Well, it's a quantum computer, so there's a lot of possibilities for being imperfect. And we've spent a lot of research effort in the last years trying to understand what's the problem is and what the outlook is for really producing high fidelity entanglement and making this scalable. And if you go back to this picture of two Rydberg interacting atoms, you can do a back of the envelope estimation of what the errors are in this gate. And it's really a trade-off between spontaneous emission errors from spending too long time in the Rydberg state, or shortening the time that the atoms are in the Rydberg state, but then running into the limit of not having a perfect blockade because the excitation frequency becomes comparable to the blockade shift. And so you can estimate the errors from those two contributions with a formula like this. This is the spontaneous emission error, which scales as 1 over the Rabi frequency times the Rydberg lifetime tau, and the blockade error, which scales as omega squared over b squared. And then you can look at this formula and just pick omega to minimize the sum of those two terms, and you get an optimum value of omega, which if you plug into here, gives you an estimate for how high the fidelity can be. And one sees that the fidelity of this entangling operation scales as the product of the interaction strength times the lifetime of the Rydberg state to the 2/3 power. So if you remember, I started by saying that the Rydberg interaction strength in the van der Waals limit scales as this high power of the principal quantum number. the lifetime scale something like n cubed. So you might expect that 1 over the product of those two to the 2/3 power, that should scale like 1 over n to the 10th. Okay, shouldn't have. And that's a naive view. Unfortunately, reality is more complicated simply because these are not isolated levels. These are Rydberg levels, and there's, at principal quantum number n, there's levels here and levels above. And so there's a limit to how much blockade one can get. It's never larger than the distance to the next level. So you don't get this 1 over n to the 10th scaling. You stop somewhere less than that. And so there's been a lot of analysis of different protocols for optimizing the fidelity of this Rydberg gate. And that's more appropriate for a seminar to go into details about those analyses. What I've been showing you, this blockade gate, in principle can be as good as 3/9 of fidelity. There's other versions of the gate, something called an interaction gate, where you excite both atoms by driving them hard and let them interact with each other to pick up a conditional phase. There's a dressing gate where one excites the Rydberg states off-resonantly, an adiabatic gate that uses adiabatic pulse shapes, a gate invented here by the Englert group that symmetrically drives both atoms, and then some more recent gates we've been working on. And so what I can tell you is that we now know how to design Rydberg gate protocols analyzed for real atoms that have the potential of getting to very high fidelity, more than 4/9 of fidelity. And let me just say a couple words about these last two variants here. So something I call a drag gate and a dark state gate. This drag gate uses some ideas that originated in the superconducting qubit community. And the idea is simply not to use constant amplitude square pulses, but to use shape pulses that are designed in such a way that we can drive the Rydberg excitation very fast and thereby minimize spontaneous emission errors, yet nonetheless not have leakage to other Rydberg states. And one can do that by shaping these pulses to put, if you will, spectral nulls in their spectrum at frequencies corresponding to transitions to other Rydberg leakage states. And so using these kinds of gates, we can get very high fidelities. Here's another recent gate idea, a collaboration with the Mulmer group in Denmark, where it uses a dark state mechanism of 2 atoms. So there's 2 simultaneously excited atoms in this gate protocol. And here the error in this gate decreases as 1 over the product of the interaction strength times the Rydberg lifetime instead of 1 over the product to the 2/3 power. So it's got a better scaling. For both of these gates, using detailed analyses with real atomic structure, we can find parameters that go below 10 to the -4 error. So we have a strong theoretical indicator that we can achieve high fidelity with these. The challenge then is to actually implement it in practice in the lab, which is something we're working towards. One aspect of these gate protocols is that they give you very fast entanglement. If I think about using a Rydberg interaction to create a Bell state by starting with a control qubit in a superposition and a target qubit in, say, state 0, this would give me this Bell state. There's a time integrated population in the Rydberg state, which is a few times the Rabi pi time, and therefore there's a spontaneous emission error, which is that integrated population divided by the lifetime of the Rydberg state. So if my target is a gate error of epsilon, I need the Rydberg lifetime to be greater than that integrated population divided by epsilon. And so just to put some numbers in, suppose I want to have a pi time of 25 nanoseconds. That gives me a gate time of 100 nanoseconds, comparable to, say, superconducting qubits. And to do that, I need a Rabi frequency of 20 megahertz. And so one can look at what Rydberg states one needs to get to certain gate errors limited by the spontaneous emission error. And this shows as a function of the Rydberg principal quantum number for different low angular momentum states and different temperatures, what the lifetime limited error will be. And so at room temperature, if I'm in a room temperature environment, I need to go up around n equals 100 to hit this 10 to the -4 error. If I'm in a 4K environment, less blackbody, less blackbody-induced depopulation of the Rydberg state, I can be satisfied with a much smaller principal quantum number and even get up to this sort of 10 to the minus 5 level. So this shows you that you need to work at these relatively high principal quantum numbers, around 60 to 100, depending on the temperature of the apparatus. We're currently working at 300 K. I will say that ultimately, I would expect that one would want to do these experiments in a 4K cryostat just to reduce the blackbody rates. Okay, so what we're currently doing in my lab is working on improving everything to make these gates have higher fidelity. We've put in place some more stable optomechanics. This is one of our most recent cells. This yellow color is the anti-reflection coating on the cell. If you look closely, there's some wires coming down the sides of the cell here. This is to connect to electrodes inside to cancel out background DC fields to prevent unwanted perturbations to the Rydberg states. We've also put in place modulators for creating shape pulses to implement some of these new gate schemes, and we're also implementing deeper cooling of our atoms with sideband cooling to reduce motional dephasing effects. So that's all stuff we're working on, and hopefully that's going to give some results in not too long. So that's sort of where we are on the experimental side of things, very actively involved in this. Let me step back a little bit and look at this in the context of quantum information and how it compares to other approaches and where the field is. So with neutral atoms, we have this potential for putting a lot of qubits together in a relatively small system and trying to use that for computation. And this is really an exciting time in the area of quantum computation simply because we truly are right at the threshold of getting beyond classical in our capabilities. And it's kind of fun, I think, to look at quantum computation versus brute force classical simulations. So large-scale classical simulators are memory limited. And so if I have n qubits, the memory I need to store the state of n qubits scales as 2 to the n. So here I plotted that memory requirement in terms of petabytes, okay? And that's this blue line here. Now, as I've learned from Google, their worldwide storage is about 10 exabytes, apparently. So 10 exabytes is 57 or so qubits if I do brute force storage. What's actually been done in classical simulators? A decade ago, there was a 37 qubit full simulation of a quantum circuit. More recently, last year, they got up to 45 qubits using a half petabyte of memory, a lot of memory. So that's running a little bit below this line. You can play some tricks and save a bit of memory, so you can come a little bit under. And then there was also, in the last half year or so, two calculations that pushed up beyond 55 qubits that are well below this line. But these were not full simulations. These were calculations of not the quantum state of the output, but the probability distribution, so a prediction of what measurements one would achieve with different probabilities. And these calculations traded off memory requirements against time. So they're limited to small depth circuits, not linear scaling for deeper circuits. And so they've pushed up to this 57 range, but certainly in this region here, a bit beyond 50 and up towards 100 qubits, we're in the regime where classical computers can no longer keep up. And we're going to see some kind of separation between the classical and quantum computational capability. So that's an interesting range to be in, and beyond this 50, 60 qubit range, and certainly different platforms are getting up to that range. Here's the scaling in the number of qubits that's being controlled with leading approaches to quantum computation, trapped ions, neutral atoms, superconductors, and quantum dots. Superconductors are now up to 20 or so qubits in published results. Ions are also around 20. The neutral atoms have in fact scaled faster than these other approaches. We don't have good 2-qubit fidelity yet, but we have a large number of qubits. And so we're certainly, all of these approaches are pushing this quantum classical divide limit. Here's a little more detail on the neutral atom scaling, a variety of experiments with different optical arrays. We're at 49 right now in my lab. We're currently working on implementing a slightly different, more efficient design that's going to give us about 120 sites. Penn State, they've done a 3D array with 125 sites. How far can you go with this? Well, you run into an optical power limitation at some point. We currently use about 20 milliwatts per qubit. This design here is more efficient in terms of trapping depth per milliwatt of laser power. That, together with some better cooling, we think we can get down to a milliwatt or less per qubit. That means you could do 10,000 qubits with 10 watts of light. So it's certainly realistic to think about large numbers with this kind of approach. We also need to scan the beams. That's another discussion, but I think there are technologies for doing that. Why are we optimistic about neutral atoms? One aspect is footprint. Our footprint for these things is relatively small, sort of 20 microns on the side, both in the 2D experiment in my lab and the 3D experiment at Penn State. It's kind of fun to compare that with, say, superconducting circuits. Here's IBM 16 qubit chip. This is a millimeter scale, and so the footprint ratio is enormous. You know, this 16 qubit chip, you could fit 1 million neutral atom qubits onto that same size, whereas 1 million of these guys is going to be a very large device. Footprint's one aspect. Another aspect, of course, is qubit quality. And I hope you'll excuse me for a little bit of advertising here, but the situation in terms of performance of these qubits is more nuanced than you might believe if you just read the popular press, which suggests that you're going to be able to buy a super powerful quantum computer at your local electronics store in the next couple of years. That's probably not the case. It's interesting to look how the fidelities have scaled as these different technologies have gone to larger numbers. So ions and superconductors have demonstrated very high fidelity for readout 1 and 2 qubit gates at small scale, but as they've scaled up, things have degraded somewhat. So here's some data for trapped ions. 2 qubit experiments have very high fidelity for these 3 operations. 5 qubit experiments are still good, but a little bit worse. Here's some data from the largest published superconducting circuits. IBM has a 20 qubit chip. Rigetti has a 19 qubit chip. You can find their data on the web at these addresses here. And these engineered qubits, superconducting circuits, they get a lot of variation as they go to these larger numbers. And that here I'm plotting both average, max, and min performance for these different capabilities. Readout in particular has been difficult to maintain at high performance levels in these larger circuits. Here's the neutral atom array, and we've actually already scaled, and that our readout and our 1 qubit gates are performing very well at 50 qubit scale. We don't have such good 2 qubit fidelity, but our challenge here is not the scaling to number. We've already scaled. It's this intrinsic gate fidelity that we're working on. And I would make the claim that as we scale this even further, that won't affect this gate fidelity, whereas it's relatively unknown what's going to happen with these other technologies. So that perspective is part of our optimism for why neutral atoms are indeed a very promising technology to be pursuing. Okay, so at the present time, we're on the verge of passing this boundary between what you can do with a classical computer, what you can do with a quantum computer. Ultimately, to really make these things scalable, you have to go to larger systems where you have error correction, which will allow for very deep circuits. And unfortunately, error correction in the quantum world is much more resource demanding than classical error correction. This laptop doesn't break down during this talk, hopefully, because it has correction hardware built in. It's got extra parity bits tacked onto every byte of information, and that overhead for doing classical error correction is something like 10%, a parity bit or so per byte. In the quantum world, we know how to do error correction, but the overhead is much more severe. It's a factor of 100 or a factor of 1,000 per bit to make a corrected logical qubit. And so the combination of universal computation and error correction unavoidably translates into a very large number of qubits. With a 200 qubit quantum computer, we can probably solve some exciting problems in molecular physics and design of quantum materials that are far beyond classical capabilities. But those 200 well-functioning protected qubits may be many thousands or even hundreds of thousands or millions of physical qubits. And so that's a real challenge. And part of that challenge in really implementing this is built into what we're trying to do with quantum computing, and that on the one hand, we want to have a collection of qubits that are strongly coupled to each other, that we have strong control over, and that are very weakly coupled to the environment. But to implement error correction, we have to remove entropy. We have to make measurements on the qubits. So we need to selectively couple some of these qubits to the environment to perform error correction. And it's challenging to couple qubits to the environment without disturbing other proximal qubits. And so let me speak to how we're going to deal with that challenge in the neutral atom setting. So to make this more quantitative, think about one of these 2D arrays of atomic qubits and say I want to measure this qubit here as part of an error correction protocol. Well, I could think about doing that by focusing a measurement beam on that atom, having a very fast lens to collect the scattered light, and then counting it with a detector. Yet at the same time, all these other nearby atoms in the array are lambda squared resonant detectors, and so that's going to give me errors in proximal qubits. And if I integrate over a 2D array, well, that error rate is going to diverge logarithmically in 2D. I have lambda squared cross-section. I have surface of my sphere is 1 over r squared. I have 2 pi r surface area, so I get a logarithmic divergence. And that error is not tolerable even for very favorable parameters of a fast lens and not too many scattered photons. So that's a real challenge for neutral atoms, and I would make the claim that this challenge appears with different technical details, but in analogous ways in other quantum computing platforms. So we've been thinking quite a lot in recent years about how to deal with that. One approach is to use two species, two different atoms, where I use, say, cesium atoms for computation, and I might think about using rubidium atoms for measurement. And what we're going to do then is map state information from cesium to rubidium, and then measure the rubidium atom as a way of making state measurements. And the resonant wavelengths for these different species are sufficiently well separated that the crosstalk problem is greatly suppressed. So we can do that using a Rydberg interaction because these highly excited Rydberg states are present in any atom or molecule you might want to consider. And it turns out if you look in detail at the energy level structure of different atoms, it's possible to get even stronger coupling between atoms of different species than between two atoms of the same species. And so I could have a computational qubit here. I could map its state onto 4 neighbors and then perform a measurement in that way. We've been setting up an experiment to do this, a dual species experiment. There's a small vacuum chamber here, and we have co-trapped, cooled and trapped rubidium and cesium atoms. And we're just now working towards doing this kind of interspecies gate. We've put in an optical dipole trap and have trapped single rubidium and cesium atoms in the same trap. These are Rabi oscillations of our rubidium atom. Here we don't have a very high loading rate, but we're doing a QND measurement of our atomic state, so we can actually reuse each atom multiple times in this experiment and get good statistics on the Rabi oscillations. We're pretty close to also doing that on cesium, so this is something underway. We think this is going to be workable, although I will say it's kind of a overhead to have all these different lasers now for 2 different atomic species. So another thought is, could we find just one atom that would let us get this separation between coherent control and dissipative operations without going to 2 species? Is there a better atom that we might use for this kind of work? So here I've colored in all the elements I'm aware of that have been used for laser cooling. in one form or another. Alkali atoms, alkaline earths, noble gases, transition metals. And in recent years, there's been a lot of activity down here with the lanthanides. And in my lab, we're working with rubidium and cesium, and also holmium, one of the lanthanide atoms. And I want to show you that this atom here might actually provide a very plausible solution to this problem of performing measurements without crosstalks in an array. So the idea is to have an atom with multiple levels where 2 levels can be used for the qubit, for example, 2 levels here, and then a spectrally isolated level that I'll call my dissipative control level D here that we'll use for cooling, for initialization, and measurements. And we do that by coupling this level up to some electronically excited state. If the frequency of the light that couples this level up here is spectrally detuned from all transitions out of the qubit states, then I have an effective isolation of my qubit levels. And if I can go coherently back and forth here, then I can have a protected qubit here and use this transition for my dissipative control. So I can quantify how well my qubit is protected by a suppression factor I'll call S, which is just the ratio of this detuning delta divided by the decay rate gamma squared. Okay? So if that factor is large for a given atomic structure, then I can have a good spectral isolation of my qubit from this level here. So we took a look around the periodic table to see if we could find a suitable atom. And you might think about a couple different choices. Well, alkali atoms, which we're mainly working with, only have 2 hyperfine levels. You can do shelving, but it doesn't scale very well. So let me discount that. Another possible choice is optical clock atoms, such as the alkaline earths or mercury. There you can have a clock qubit at an optical frequency, say from a singlet S to a triplet P level. And then I could transfer this triplet P state to another excited state and then cycle that on a P to D transition as a way of performing this kind of isolated measurement. It turns out if you look at the atomic structures in detail, you find either that this is at a very long wavelength, which it's hard to count photons, or there's leakage channels. Actually, magnesium looks the most promising here, although laser cooling has proven difficult in magnesium. So that's one possibility. And then the lanthanides turn out to be another one. And the lanthanides have multiple hyperfine ground states, so they're kind of ideally suited to implementing this kind of structure. So we went through and looked at all the lanthanides, and it turns out there's 4 isotopes that are promising. One of the erbium isotopes, 2 dysprosium, and then holmium, which just has a single isotope. There's a lot of numbers here. This is some work that we're just writing up right now. But what I'll tell you is that the suppression factors can be very large. The spectral isolation suppression factor can be a few thousands up to 10,000 in holmium for the strong Doppler cooling lines. There's also narrow line transitions in these atoms for getting to lower temperatures. And those narrow lines have suppression factors of a few billion for all of these atoms. So we can get a very effective spectral isolation. So the last couple of years in my group, we've been doing laser cooling of holmium. You can actually make a very simple MOT. You don't need a repumper. It just takes one laser. So we easily get MOTs with 1 million atoms or a few million atoms. We've also done Rydberg spectroscopy on this atom and identified well-behaved Rydberg series. And we now have a fairly complete theory of the Rydberg interaction of these more complex atoms. And so we've started working on optical trapping of these. And here's some recent unpublished data showing dipole trapping of a few holmium atoms in a red detuned trap. And yes, we can dipole trap these atoms, but it turns out dipole trapping is not so great in the lanthanides for quantum information because there's too much angular momentum. The ground state, unlike the alkaline earths or alkalines, is a large value. So holmium has J 15.5 in the ground state, and so there's a lot of tensor polarizability. And that tensor polarizability means you're going to get different light shifts on different qubit levels, and it will give poor coherence properties. So this is the scalar polarizability. We're working right here right now. This is the ratio of tensor to scalar. And there might be one region which is promising, but it's a little uncertain right now. So therefore, we've looked at magnetic trapping. And in holmium, you have all the states, all the hyperfine states have positive G factors, positive Landé factors, so they're all weak field seekers and can be magnetically trapped. And so there's 60 magnetically trappable states. So we've calculated the Wright-Rabi spectrum for holmium and identified pairs of states that have the same Zeeman shifts and therefore can give good coherence properties, so-called magic trapping conditions. And there's 85 pairs of states that are magic at magnetic fields under 2,000 Gauss. Well, we don't want to work at that high a field. That's inconvenient for making an array. It turns out there's a particular pair here which has a magic condition at just 3.5 Gauss. And that's because if you go to LS coupling, the states F equals 5 and F equals 7 have Landé factors in a ratio of 5/7, and therefore the maximal M states with M equals 7 and 5 have the same linear Zeeman shifts. You add in a little bit of nuclear magnetic moment, and you find this small field magic condition, which should give coherence times of many hundreds of seconds. So what we're considering here is this pair of states as a qubit, which can be magnetically trapped and be insensitive to noise, and then the F equals 11 state up here for our dissipative control, giving these very large spectral isolation factors. And interestingly, we can have this pair of states magic at 3.5 Gauss. If we add microwave dressing fields, we can make all of these states with maximal M for each F be simultaneously magic by microwave dressing them with respect to the next up F level. And so one could think about implementing qubits in this system, which is another plausible approach to making error correction more favorable using these higher dimensional quantum encodings. So we've been looking at magnetic trapping and designs for magnetic trap arrays, and we've come up with a design which builds on some older work from the Fowl group of having a two-dimensional array of Yoffie-Pritchard traps. We have a construction here with 2 layers of wires to create the magnetic fields. That combined with an external bias field gives you a 2D array of 3D traps. And what we're then going to do is etch holes through the substrate under each atom for the optical access for Rydberg excitation. So we've been engaging in discussions with our local nanofabrication facility for the last year, and we're edging towards trying to make our first versions of some of these chips in a small scale. This, if we can get everything to work well, has the potential of getting beyond this optical power limit that you have in the optical trapped arrays and potentially going to very large scalable systems. So that's something we haven't published yet. I'm a strong believer in that if you come to a talk, it should be some added value. That is, you get to hear about something that's not written up. And so this is one of the things we're excited about right now that we're working on, hopefully in not too long. So let me summarize then. I've told you about neutral atom quantum gates, and we've made a lot of progress. There's still a lot of challenges ahead of us, but we're optimistic that we can solve them. Looking even further in the future at some of these crosstalk challenges involved with implementing error correction, we're thinking hard and working on different solutions. One is this dual species approach that I said a little about. Another is going to more complex atoms such as holmium and thinking about magnetic trap arrays. And all this work wouldn't be possible without a talented group of postdocs and students who work with me in Madison. This is most of my current group. And let me thank you for your attention.